Let's look at this right triangle with the length of 3 sides being 3, 4, and 5. And we already learned how to find the 6 trigonometric function values for this acute angle theta. For example, if I want to find out sine theta, since sine theta equals to the opposite side over the hypotenuse side, therefore 3 over 5, sine theta equals to 0.6. However, what if I want to find out what this angle is? Is it 30 degree or 45 degree? How do I evaluate the size of this angle? If you recall, we learned about the exponential function, a raised to the power of x equals to y, and if we want to solve for the exponent x, we can use logarithm x equals to log ay, and the logarithmic function is the inverse function of the exponential function. So can we find something similar for the trigonometric function? So if we can find this inverse sine function, then if we know that the sine value for an angle x is y, which is the side ratio, then we can use this inverse sine function to solve for our angle x, and that can be very helpful. However, don't forget all 6 trigonometric functions are periodic functions. Therefore, if we look at the graph for the sine function, we realize that it does not pass the horizontal line test. And based on our previous knowledge, sine function cannot have an inverse function. But since it is very useful to define the inverse sine function, we're going to do so for only a small segment of the sine function. Now, for this segment of the sine function, as you can see, it does pass the horizontal line test, therefore it will have inverse function. Therefore, for the purpose of defining the inverse sine function, we only focus on this segment of the sine function that x is between negative half a pi and positive half a pi, and that is also the domain for this segment. The range is the same as the sine function, it's negative 1 to positive 1. And since we learned before that the graph of the inverse function is the reflection of the original function with respect to the 45-degree line or the y equals to x straight line, therefore we can sketch the reflection here, and this blue curve does represent the inverse sine function fx equals to sine inverse x. It can also be written as fx equals to arc sine x. These two notations can be used interchangeably. Once again, this is the graph for the inverse sine function, or fx equals to arc sine x. As you can see, the domain for this inverse sine function is the range for the original function, which is between negative 1 and positive 1, including both ends. And the range for this inverse sine function is the domain for the original function, which is between negative half a pi to positive half a pi. It is very important to remember this range, because this tells you that when you use the inverse sine function to calculate for an angle, you can only get an angle that is between this range. So if we want to evaluate, say, f1/2, which is to find the value for arc sine 1/2. On the graph, we can read the y coordinate to be 6 pi. This indicates that f1/2 or arc sine 1/2 equals to 6 pi. Why? Because sine 6 pi equals to 1/2, and because 6 pi is between negative half a pi and positive half a pi. If you remember, there are unlimited numbers of coterminal angles for which the sine value is positive 1/2. However, arc sine 1/2 can only equal to 6 pi. These two conditions must be satisfied simultaneously. Therefore, to answer our original question, now we can find this angle theta to be arc sine 0.6 or sine inverse 0.6, and you should be able to use your calculator to evaluate theta to be approximately 36.87 degree. Similarly, if we look at the graph of the cosine function, we won't be able to define the inverse function for the cosine function because, once again, the graph does not pass the horizontal line test. Therefore, in order to define the inverse cosine function, we are again going to focus on only this segment of the cosine function, which is between 0 and pi. So for this segment of the cosine function, it has the new domain that x is between 0 and pi, including both ends. The range is still the same, from -1 to +1. And now it does pass the horizontal line test, therefore we can define an inverse cosine function. And again, we know that the graph should be the reflection of the original function with respect to the 45-degree line. And we sketch it. And this curve represents the graph of fx equals to cosine inverse x, or fx equals to arc cosine x. Again, this is the graph for the inverse cosine function, or fx equals to arc cosine x. It has the domain from -1 to +1, including both ends, which is the range for the original function. And the range for this inverse cosine function is from 0 to pi, including both ends, which is the domain for the original function. Once again, it is important to remember this range because this indicates that if you use the inverse cosine function to evaluate angles, you can only get angles back that are between 0 and pi. So, for example, if I want to evaluate f -1/2, which means that I want to find out the value of arc cosine -1/2 from the graph, I can read the y-coordinate of 2/3 pi, which indicates that arc cosine -1/2 equals to 2/3 pi. Once again, this suggests that not only because cosine 2/3 pi equals to -1/2, but also 2/3 pi is between 0 and pi. Once again, these two conditions must be satisfied simultaneously. Once again, in order to define the inverse tangent function, we're going to focus on only this period here from -½ pi to +½ pi. Therefore, for this first period of the tangent function, its domain is the open interval from -½ pi to +½ pi. It cannot include the two ends because those are the vertical asymptotes of this tangent function. And its range again includes all real number. Therefore, we draw the 45-degree line and draw the reflection about this line, and this blue curve is the graph for the inverse tangent function, or the arctangent function, arctangent x. Therefore, for the graph of the inverse tangent function, you can see that the domain now includes all real number, and the range is the open interval from -½ pi to +½ pi. And again, it is important to remember the range for the inverse tangent function. Now it has horizontal asymptotes that y equals to either negative or +½ pi. And we can also use this graph to evaluate, say, f1, which means that we want to find the value for arctangent 1. From the graph, we can read that f1 equals to ¼ pi. Again, this is because not only because tangent ¼ pi equals to 1, but also ¼ pi is between -½ pi and +½ pi. Once again, the two conditions must be satisfied simultaneously. Let's look at this example to find the exact values of these two expressions involving inverse trigonometric functions. When you are using the inverse trigonometric functions, don't forget the purpose is to solve for angle. Therefore, for example, for part A, we're looking for an angle theta that equals to the inverse cosine of -√2/2. What does that mean? It means that there are two conditions we must satisfy simultaneously. First, cosine theta must equal to -√2/2. And secondly, this angle theta must be between 0 and pi. Therefore, there's only one angle that satisfies these two conditions, and that is 3/4 pi. For part B, similarly, we are looking for an angle theta that equals to arctangent √3. What does that mean? It means that, once again, not only does tangent theta equals to square root of 3, but also theta must be between negative half a pi and positive half a pi. So there's only one angle that satisfies these two conditions simultaneously, and that is third pi. Let's look at this example to determine the exact values of these two expressions. If we pay attention to these two expressions, because of their format, we might be tempted to apply the inverse property directly and get 2 pi and a negative 6 pi directly as answers. However, don't forget, the inverse trigonometric functions are defined specially. Therefore, we shouldn't jump into applying the inverse property. So, let's look at part A. Since sine 2 pi equals to 0, therefore, for this part, we are simply asked to find the inverse sine of 0. Therefore, this becomes similar to the previous example. We're looking for an angle that equals to inverse sine 0, and based on this, we know that not only is sine theta 0, but also theta is between negative half a pi and positive half a pi. Therefore, the only angle that satisfies these two conditions is theta equals to 0. As you can see, the answer is not 2 pi. Similarly, for part B, because cosine negative 6 pi equals to square root of 3 over 2, therefore, for this problem, we are looking for arc cosine square root of 3 over 2, which means that we're looking for an angle. And what do we know about this angle? We know that cosine theta equals to square root of 3 over 2, and theta is between 0 and pi. Therefore, theta can only be positive 6 pi. Once again, the answer is not negative 6 pi. Let's look at this example. Again, we need to determine the exact values of these two expressions, but this problem is a little bit more complicated when compared to the previous two examples. Let's look at the first one here. We need to find tangent within the parentheses sine inverse 1/3. Now, we know that the output of an inverse trigonometric function is always an angle, because inverse trigonometric function is used to calculate angles. Therefore, sine inverse 1/3 is an angle theta. Although we don't know what angle theta is right now, we know that we need to find tangent theta. So what do we know about this angle theta? We know that sine theta must be 1/3, and because it is the output of the inverse sine function, therefore it must be between negative half a pi and positive half a pi again. And that tells us that this angle theta must be either in quadrant 1 or quadrant 4, and of course it could be along the y-axis as well. But once again, since sine theta is positive, that narrows it down to only quadrant 1. So we know for sure that theta belongs to quadrant 1, and therefore tangent theta must be positive as well. So now, based on this information, we can draw our right triangle and use our reference angle theta prime. We calculate this side right here. Therefore, tangent theta, because it's positive, it equals to positive 1 over 2 square root of 2, which is square root of 2 over 4. And that's the answer to part A of this problem. For part B, similarly, we know that cosine inverse negative 3 over 7 is an angle theta, and we know that we need to find tangent theta for this problem. Now, what do we know about this angle theta? Because theta equals to inverse cosine negative 3 over 7, therefore, cosine theta must equal to negative 3 over 7, and at the same time, theta must be between 0 and pi. Therefore, theta must be in either quadrant 1 or quadrant 2, or it could be along the x-axis. But since cosine theta is negative 3 over 7, that narrows it down that angle theta can only be in quadrant number 2. Therefore, we can tell that tangent theta in quadrant 2 is also negative. With all that information, we can draw our right triangle, mark the correct sides, calculate this last side here, and using this reference angle, we can determine tangent theta to be negative 2 times square root of 10 over 3. It is negative because, once again, we determined that angle theta is in quadrant 2.